Okay, who doesn't just like to say the word haboob? Really? Pretty cool. So what is a haboob? A haboob is an extremely large sand dust storm, and they do happen in the United States, probably more often in the Middle East. But how does a haboob develop, and what causes it, and what are the issues with it? So think about first some type of thunderstorm happening out in the desert. Same complex, updraft, downdrafts. Oftentimes with these thunderstorms, though, they're almost like dry thunderstorms, is that the rain that's falling out of this thunderstorm cloud may actually evaporate before it hits the ground, and rain that never touches the ground is what's called virga, or precipitation that doesn't touch the ground. But you have the updrafts, you have the downdrafts. As it comes down, it either evaporates, but it's still a water vapor, and then it turns around and rises back up, which creates that updraft again, which pulls up all that sand and dust really back up to the very, almost to the tropopause. And that's why you can go up to 30,000 feet with this big, huge dust storm. Usually short-lived because it doesn't sustain its energy. That T-storm doesn't have the moisture recycling over and over and over again to sustain it. So haboob is a giant dust storm. Could be up to 30,000 feet, so it would affect planes. Very relatively short-lived, maybe an hour or two. And probably the biggest issue with haboobs is the visibility issues that cause car accidents, etc. It can cause respiratory issues if it sustains a lot. People are caught outside. But that's an haboob. Okay, let's talk a little bit about hurricanes. Let's see. First of all, extremely low pressure weather systems. Again, excuse my artistic lack of talent, but let's call this Africa, let's call this North America. Dotted line being the equator, next dotted line being roughly 30 degrees, so we're talking about Hadley cell. And we should know by now within the Hadley cell, the prevailing wind, what are called the trade winds, right? Or sometimes called the easterly waves. Easterly wave, say it again, easterly wave. And that's what's going to push these. So you start getting a little low pressure development off the west coast of Africa. Initially what's called level 1. This is going to be called a tropical disturbance. And this is turning again, in a, excuse me, counterclockwise fashion. But it's just a little low pressure storm beginning to develop off the west coast of Africa. Trade winds began to push it along. Warm Atlantic waters near the equator provide the energy to continue to develop this. They need to be at least 80 degrees Fahrenheit. That is why hurricane season is late summer, early fall. Because it takes that long to heat up the water. Remember, the specific heat of water is much greater than that of land. So it takes a lot longer to raise that temperature, but also takes longer for it to cool off as well. So it needs to be the easterly wave, tropical disturbance moves, picks up energy from that 80 degrees, so that hot water begins to evaporate, rise in stability, weak shear. You don't want a lot of wind shear on a hurricane because they'll kind of chop the top off of it off. So as it progresses, it goes from a disturbance to a tropical depression. It gets stronger. Tropical depression, winds up to 38 miles per hour. And it continues to move westerly, and it's getting stronger and stronger and stronger. It gets over 38 miles per hour. It now becomes a tropical storm. Tropical storm anywhere between 39 and 73 miles per hour. And also, when it becomes a tropical storm, it gets its name. Every year, the National Hurricane Center creates names. They start with the letter A. They go boy, girl, boy, girl, boy, girl, until they run out. If they run out of names, they go to Roman numerals. Interestingly enough, if a hurricane were ever to cross over, let's say, Panama and into the Pacific, the name changes because Pacific hurricanes get to have different names than Atlantic hurricanes. Very much a rare factor. So as it continues along, it's moving towards us, the Caribbean. It's picking up energy, it's picking up speed. The wind speed gets up over 74 miles per hour, officially becomes a hurricane. The scale used to classify hurricanes is called the Saffir-Simpson scale. There's categories 1 through 5 based on wind speed primarily, but also does include central core pressure and storm surge is included in those 3 things. So it's not just wind speed, but primarily wind speed as it moves along. So as it gets closer to here, and again, it is turning in a counterclockwise fashion, gets stronger and stronger and stronger. There is something out here occasionally that helps steer this. This is going to be your Atlantic Ridge. Remember the high spot of a high cell, or the other name is called the Bermuda High. So the Bermuda High can often be a steering mechanism depending on, it does fluctuate during the year, so depending on where it is, it could push it into the Gulf, or it could allow it to come up the east coast of the United States. A little bit of the anatomy of a hurricane. Again, the central core is called the eye of the hurricane. And generally the smaller the eye, the tighter the eye, the more intense it is. It's like that figure skater closing their arms and they spin more rapidly. The outer edge of the eye is called the eye wall. It is the most intense part, and that's where the strongest winds are. Then you have rain bands along the edges, and actually there's a layer between the eye and the rain bands, and they call that the hurricane moat. Think of the moat like a castle surrounded by water. The rain bands, more water, so the moat is really between the eye wall and the outer rain bands. That's a little trivia for you. So it's turning in a counterclockwise fashion. It gets its energy from the water temperature. As it comes over land, it's going to lose that water, and it's going to get friction, and that's going to break down that hurricane. With Hurricane Sandy, Superstorm Sandy, also Frankenstorm Sandy, Sandy's path came along here, it turned up here, the coast, and rarity was this, there's another high up here, the Icelandic high, that was hanging out there, and generally at this time of year, it's more to the east, but it was hanging right up there over Newfoundland, and that was really what was called that blocking high, and it's turning in this direction. Was one of the few things. 9 times out of 10, those hurricanes are going to turn out here and kind of die off in the northern Atlantic. With Sandy, that high was actually a little bit lower. It was here and made that turn into New York. Again, it was late in the year, October 30th, Halloween. It was also high tide, very populated area, which became a very dramatic storm. And also, after it gets to a certain position where the warm waters are no longer fueling it, it actually becomes what's called a post-tropical hurricane or a post-tropical cyclone. And in that particular case, it actually banded with another storm. So that's hurricanes kind of in a nutshell, so you understand how they turn, where they form, the levels, basic anatomy of a hurricane. All right. Okay, so we talked about squall lines already a little bit. But want to get a little bit more in detail about some of the winds produced by thunderstorms, and then we're talking about non-supercells because we know supercells actually rotate. But again, from a T-storm function, you have warm updrafts, cold downdrafts. This heavy downdraft creates in the front edge what we call a gust front. That's that leading edge of wind of a T-storm. A long line of thunderstorms called the squall line. So they have that, what we call straight line winds, versus a tornado, which has a rotating wind. So when we talk about straight line winds, the kind of the catchphrase for all those could be considered downburst, because the wind's coming basically straight down and it's all in one direction versus a rotating mass. So how do you classify downburst? Well, a microburst is where that line of wind is 2.5 miles or less in width, if you will. So that's a microburst. A macroburst when it becomes over 2.5 miles. And in the cases of a derecho, which would be huge winds along a long extended squall line greater than 240 miles long. And when we had that East Coast derecho, it basically covered 4 to 5 states at one point in time, traveled across 13 states. A derecho combination needs to have be at least 240 miles wide and have winds in excess of that same wind speed, which is severe storm wind speed, of 58 miles per hour. So, T-storms can produce straight line winds, downbursts. If they're less than 2.5 miles wide, they're called microbursts. Greater than 2.5 miles wide, macrobursts. In a case where the wind speed is exceeding 58 miles an hour and that line is greater than 240 miles, it's called a derecho. Okay, we're almost done here. So last one to think about, I guess, for now. I may have more, but don't hold me to that. Orographic lifting. So here we have water. Let's think of this as the west coast of the United States, if you will. So this could be California or Seattle. But here's water out here coming in. So that's going to be what? Maritime tropical, maybe maritime polar air masses moving in, but it's moist air coming in. And so as this air comes in and it hits this mountain range, it can only really go one way, so it forces it up, which is called orographic lifting. So as it forces it up the mountainside, and as we know now with adiabatic heating and cooling, as you go up, the pressure gets less, the temperature gets colder. More times than not, you get a lot of condensation and rain up here. As it gets cooler, the moisture can't be held in that, clouds develop, it rains. And that's why Seattle is one of the wettest places in the United States, is because of the orographic lifting. So now it comes across the top of the mountain, and this air mass now has lost most of its moisture. And if we go back to specific heat, we know that it takes more energy to change moist air or water than it does dry air or anything else. So as it's lost all its moisture, as it comes across the top, it comes rushing down the other side, coming down, and we know, going back to adiabatic heating and cooling, as it goes down, the pressure is going to increase anyway, so the temperature is going to increase. And because of it's dry versus moist, it's going to increase even more and rapidly. So you get this very dry, hot air coming down the other side. These are called foehn, that's an E, foehn winds, and if this is the Rocky Mountains, this is called a Chinook wind. Alright, so orographic lifting, rain on this side, sometimes they'll call this is the rain shadow side, and for mostly popular, we know that the water side is called the windward, and the dry side, or opposite of windward, is called the leeward side. So orographic lifting means you need a physical body, like a mountain. It requires to go up, drops all its moisture. As it cools, it goes up. Because it's dry, it increases temperature even faster. So moist, cool, hot, dry. Chinook wind, if you're in the Rockies, a foehn wind is anything on the leeward side, and they often call this side, the opposite of the rainy side, is the rain shadow side. So that's orographic lifting, foehn winds, and how it impacts our weather.